Finally, for part B of this problem, this zinc nickel electrochemical cell, zinc hydroxide on the anode, nickel oxide hydroxide and nickel hydroxide on the cathode. If the cell voltage is 1.3 volt, the problem wants the current density. What would be the current density so that the overall cell voltage, which is still in galvanic cell because 1.3 volt is smaller than the equilibrium cell potential, which is 1.74 volt. Okay, and in galvanic cell mode, if the cell total voltage is 1.3 volt, what the current would be? Okay, and we know the cell actual voltage would be equilibrium minus the contribution of anode over potential, cathode over potential, and the ohmic loss, uh, primarily from the electrolyte, which is equivalent to calculate the condition, the current that would give us the anode over potential and cathode over potential and ohmic loss to be the equilibrium cell potential minus this galvanic cell potential, 1.74 minus 1.3, which is 44 milli 440 millivolt or 0.44 volt. Okay, so same as before, we can set it up still in Excel, and for the zinc electrode, we have the roughness factor, we have the exchange current density, transfer coefficient for anodic and for cathodic for the zinc half cell. Similarly for nickel roughness, nickel exchange current density, anodic cathodic transfer coefficient for nickel. And then in this case, we also add electrolyte conductivity kappa 60 Siemens per meter and electrolyte thickness in unit of meter, which is 0.002 meter or 2 millimeter. Okay, and like before, we can provide initial gas for eta A zinc, eta for over potential, A for anodic zinc, and 0 eta C zinc, over potential, and cathodic for nickel also to be 0. That's our initial gas. And with this initial gas, we can calculate by Bartlett-Wohlmer equation the current density on the zinc electrode. If the over potential is 0, not surprisingly, the current density, the net current would be 0 on the zinc anode. And if the nickel over potential is 0, the net current on the nickel electrode would also be 0. And this cell F82, this cell calculate the summation of nickel and and zinc anode and the nickel cathode. But remember, one in principle should be positive, one in principle should be negative, and then we take the absolute value. Here it will be 0. And J absolute value takes the average would just be JA minus JC. You take absolute value divided by 2 and still is 0. So again, as we said, for initial gas the over potential, we just as the starting point we just do 0 and 0 for zinc anode and for nickel cathode. Zinc anode is in cell A81 and the nickel cathode over potential would be in cell D81. And then this cell F83 gives a difference in absolute value between the anodic, or people say positive current on zinc, and the cathodic or negative current on nickel. And the difference should be very small. So one JA should be positive, JC should be negative. You add them up, the arithmetic summation should be a very small value, and in this case we want to be smaller than 1 amp per meter square. And this one is absolute current average, which is JA absolute plus JC absolute divided by 2, or you can consider JA and JC are opposite value with just JA minus JC absolute value divided by. So with these, we can still use Excel solver to provide fitted values for eta A zinc anode over potential, eta C nickel cathode over potential, and they are stored as we said earlier in cell A81 and cell D81 respectively. Okay, and as you use Excel solver, our objective as you see would be for cell B84, which is cell voltage to be 1.3. Initially, if overpotential is 0, current is 0, then the cell voltage would be equilibrium cell voltage, of course, because this cell voltage is calculated as an equilibrium minus the absolute overpotential for zinc anode, absolute overpotential for nickel cathode, and absolute ohmic loss, which is this term. Okay, so you set up the Excel and using solver, the objective is for the cell voltage EGC in cell B84, which is also here B84, to be the value. This time we are not trying to make it the maximum or minimum, we are trying to make it to be the exact value of 1.300 volt. Okay, and then Excel solver asks you to define the cells to be changed or the cells to optimize. Then we have by changing cell A81, which is eta A zinc zinc anode over potential, and cell D81, which is eta C nickel cathode over potential. By changing these two cells to give the objective of EGC cell galvanic cell potential of 1.3 volt, and to help the fitting, we also added a few conditions, or so-called constraints, subject to the constraints. And the first two are for the overpotential eta A zinc, which is cell A81, in the range from 0 to 2. Why? Because we said zinc is our anode and it's going through anodic polarization, so the overpotential should be positive from 0. Let's make it 2. Okay, actually it should be 1.74. Similarly, the EC nickel, which is cell D81, overpotential for nickel cathode, because it's cathodic overpotential, we set it to be from -2 to 0. Actually should be -1.74 to 0, considering this cell open circuit potential. Our equilibrium is only 1.74. And finally, for cell F83, which is the JA plus JC, and the absolute value, it should be smaller than 1. Meaning JA and GC are close in absolute value, but with opposite sign. Okay, the close in absolute value, but opposite sign. So with these conditions, using Excel solver, we have a objective or target to make our EGC instead of 1.74 to be 1.3 by changing overpotential on the zinc anode, overpotential on the nickel cathode, and subject to 3 additional conditions. The anode overpotential from 0 to 2, the cathode overpotential from -2 to 0, because cathodic it should be negative, and then the current absolute value difference. If you one positive, one is negative, you added them up. That's actually the difference in absolute value. It should not be very large. And let's say make it 1. Okay. Then with Excel solver, if you set it up, and it will find a solution. It will find a solution. Excel solver find a solution and show here. The objective EGC, which is cell B84, B84, now it indeed became 1.300 volt. And now the optimized or adjusted eta A zinc zinc anode overpotential is indeed a positive number, 0.0627 volt or 62.7 millivolt, and it's positive, indicating anodic overpotential. On the other hand, eta C nickel, the cell D81 would be minus 0.2226 or minus 222.6 millivolt, and its minus means cathodic overpotential for nickel. Okay, and under this condition, the anodic current on the zinc electrode, you see, would be positive 4641.1 amp per meter square anodic current density, and at this cathodic bias on the nickel electrode, the cathodic current would be minus 4640.1 amp per meter square. So minus sign for cathodic current. And of course, the Ja plus Jc F83 cell absolute value, the difference between absolute value for the Ja and zinc electrode, Jc and nickel electrode is pretty small, only 1 amp, which means the solution is pretty close to reality. Okay.